Okay, so my name is Zhe. I'm a research scientist from Google Research, and part of my research interest is multitask learning and transfer learning, mostly for search, ranking, and recommendation problems. And part of my work is conducting research and prototyping new techniques in this field. And the other part of research is actually try to understand and apply these new techniques we developed on real Google production systems. So all of the work has built on TensorFlow, and we also have an internal library and inside with TFX. So I'm going to talk about multitask and transfer learning, and mostly I'm going to introduce some of the basic concepts and some of the use cases we run into, and some of the challenges we have and we are planning to solve. So basically, different from many of other traditional machine learning problems, machine learning in real production systems as well as in real life usually involves multiple objectives, and you need to learn that maybe in different stages. That's true for us human beings because we need to do this multitask since the day we're born. At daytime, we need to write programs. At nighttime, we need to walk our dogs or talk with friends. And similarly, a powerful machine learning algorithm should have this in mind, have this ability as well. It can do multitask learning as well as transfer learning. So here in our definition, multitask learning is actually referring to the concept of learning multiple tasks in a single model. Well, transfer learning usually referring to learning target task by transferring the knowledge from the source task. So there are many other different versions of definition of multitask learning and transfer learning. Sometimes they overlap with each other. However, in our definition, the difference between the two can simply be shown on this figure. Where transfer learning only cares about the source task, the target task, you can do whatever on the source task to transfer the knowledge from them to only improve on the target task. While multitask learning, we care about all of the tasks. We need to have a model that can perform good on every task. Even though they have these differences, however, the challenges and benefits are most of the time shared. In the sense of benefits, so by doing multitask learning or transfer learning, by learning many tasks, it can enforce that we can learn a better shared representation knowledge so that we can improve the performance. And it also enables using one model to perform different tasks. This is mostly true for multitask learning, and also is very practical for production systems because the cost of maintaining many serving and training infrastructure for different models is sometimes unrealistic. Last but not least, even tasks with sparse data can be learned by transferring the knowledge from tasks with larger number of labels. This is true for both multitask learning and transfer learning. So the rest of the talk is going to be surrounded on two case studies, one for transfer learning and one for multitask learning. And I'm going to talk about the content recommendation problem as a case study of how we use multitask learning and how we see challenges in multitask learning and how we improve that. So a recommendation system is quite important in Google. That usually takes the input of users, some items we want to recommend to users, and some of the context, and provide a rank list of items to be recommended to user. So taking an example here as a video recommendation, we want to recommend a list of videos based on users' interest, given what the user's past watch history is, and also given some of the context, like the current video the user is watching, or maybe the time of day or the location of the user. And a machine learning algorithm can definitely help in the sense of predicting users' interest given the item. And to actually learn this large model, we need to learn billion users' interest on billions of item space. Therefore, we need tens of training data. The source of training data we use mostly are users' activities or behaviors from the logs. For example, if user click and watch some of the video or user engaging with the video item, we use that as a training signal to train the model to learn the probability of user going to engage with this item. However, user engaging with that item is important. Also, we want to know the item or the video we recommended to user after users clicking is what they actually like. Therefore, we also need to capture signals from other types of user behaviors or activities like users like or dislike a video after user click the video, or whether user dismiss the video simply because users just don't like it to be shown on the recommendation panel. Therefore, we need to have a machine learning model, basically a ranking model, to learn two types of tasks, the engagement task and as well as the satisfaction task. And the list can go on and on if we want to learn more signals to make the recommendation or ranking model even more powerful. So to solve this, we usually have this learning to rank model, where it takes the input of users' features, the item features, both content and topic and metadata, as well as some of the context features, and try to generate predictions of different targets. And then we combine the targets together to provide a final ranking list. So in the deep learning world, what we usually do is to use this model proposed somewhat 20 years ago, which we call shared-bottom model. Where you can see it's quite straightforward. Where in a deep neural network, you share several bottom hidden layers to learn the shared representation, and then you have separate towers for each of the tasks, so that the task can learn their own representation. This turned out to be worked relatively well, as has been launched in many systems, including the video recommendation system. You can see that in our Rex's 2016 paper. And the reason why it works really well is that one explanation is that it kind of related to the inductive bias and regularization point of view, where by learning multiple tasks together, you actually have this implicit data augmentation, meaning that you'll see more labels, even not the labels from the same task, but probably highly related tasks. Also, it enforces attention focusing, meaning that when you're training your machine learning model, in the training data, there's a lot of noise. By learning the multiple tasks together, you kind of focus on most important information other than noise. And also it enables eavesdropping, meaning that there are some tasks that are harder to learn simply by itself. But if you learn a hard task with an easier task, by learning them together, you can learn better on the hard task as well. Last but not least, because different tasks can treat each other as a regularization term, in the sense of you have different laws in this model, it enables regularization so that you can learn a better shared representation. And through this time, we have seen this model works relatively well. However, there are still a lot of problems where we're thinking about whether using multitask learning is doing a win-win situation or have a trade-off or zero sum. And the reason why we're saying that is because we observe the shared-bottom model is very sensitive to many factors. It's quite data dependent. For example, like the task relatedness, and also the different distribution on training data, and also as well as the labels can affect where and how the shared-bottom model can learn very well or very bad. And also, basically, it means that whenever we have a shared-bottom model, we can simply increase the weight on maybe task 1 and have a better task 1, but it's quite impossible to not hurt task 2. So therefore, we conduct several research on how we can resolve this conflict, or basically when we are updating the different losses, there are conflicts of different laws on the shared representation, and how we can better resolve this by modeling task relationships. One observation we have is that we conduct this experiment on synthetic data, where we can actually, using the shared-bottom model, where we actually can control the correlation between two tasks, where we can see the loss of one task significantly increase when the correlation of the two tasks are low. And at some time, it even worse than just training it by itself. So how we can do better by on multitask learning, by have a flexible modeling architecture to model these task relationships. So what we do is that we explore different model architectures, and we propose what we call multi-gate mixture of expert model, which changing the shared-bottom architecture looks like this. So basically we do is that we make two modifications on the shared-bottom model. First, we introduce mixture of expert layers. So mixture of expert layer has been recently very popular, being used into all kinds of machine learning applications like image, tag, and NLP. So basically, it enables modulation on the hidden embeddings, where you force each of the expert to learn different part of information from the inputs. And the second modification we make is to add gating networks to select experts. And in this case, each of the tasks will have their own gating network, meaning that they can select which expert to share due to task commonality, and select which expert they're going to use for themselves due to task conflicts. So having this model architecture, we do the same experiments on synthetic data, where we show that we have significantly improvement on the loss, even the correlation is low. So next, we're going to talk about how we're going to apply this on some real Google production system for content recommendation. So some of the system has been looking like this, as I just mentioned before, which is the shared bottom model. We changed some of the shared hidden layers into this mixture of experts layers, and we keep the separate towers on the top. And here is the live performance shown here. So basically, the first column is that so basically we're doing this A/B testing, and the first row shows that we're comparing a shared bottom model with a single task model. Just care about the engagement metric, where we can see having the shared bottom model, we improve significantly on the satisfaction metric, because the model also learns about satisfaction, like whether users gonna dislike or dismiss or like that. But it hurts a lot on the engagement metric. So just one thing to mention is that because the volume of the engagement data is much, much larger than the volume of the satisfaction data, usually like 20% is huge, but on the engagement metric, 0.2% is also very huge. And next, we apply this multi-gate mixture of expert architecture and comparing that with the shared bottom model, where we can see further improvement on both of the tasks with a quite significant amount of number. To further visualize whether this mixture of expert architecture works, we also plot this graph to show the importance of each of the tasks shown. So on the x-axis is the expert's ID. So here we have 4 experts, and y-axis is actually the importance of each of the tasks on the gating network. Because we have a softmax gate, basically it means that the probability of each of the tasks use each of the expert. So you can see the engagement task, because that's the main task, or because that's it has the majority of the data, usually utilize all of the experts. While satisfaction data, because it has much less volume, use only one of the experts more importantly than the others. So to sum up the multitask learning part, we see that the existing work on multitask learning facing all of the challenges, for example, is quite data dependent, and also different model architectures, even for MMOE, is still quite sensitive to this task relatedness, also the distribution of the training data, as well as the task labels. And we've been doing research on how we can do better parameter sharing to model these task relations and conflicts. And of course, multitask learning is quite important, has been used on multiple Google productions for ranking recommendation or any type of general joint classification or prediction problem. So now we're going to switch gear to talk about some transfer learning approaches and use cases, where we can see it shares a similar challenge as multitask learning, where all of these machine learning algorithms are quite data dependent. It's also based on the factors of the ratio, for example, between the source task and target task. And the research here actually, because the difference between transfer learning and multitask learning, here we only care about the target task. Some of the research we've been working on is how to figure out the better parameterization on the model parameters, so that it not only model the task relations from source to target, it also make best use of it for the target task. And there are also many use cases. For example, any use case with sparse label or few number of labels which cannot be learned by using the complicated machine learning model, can be learned by transferring the knowledge from a larger set of labels from other tasks. And the case study I'm doing here is user response prediction. So coming back to the recommendation and ranking problem, what we really want to do is to provide a rank list of items that users are interested at. So the ultimate goal is actually to predict users' interests. However, because our model requires a large quantity of training data, what we are using is called implicit feedback, which are users' activity or logs, such as click, like, dislike, and dismissal. We have billions of them, so we can train complicated deep neural network models. However, more accurate training data would be users' responses from survey that we directly provide this user and to this user an item and asking for his interest, whether he's going to like it or not. However, we only maybe have a couple thousands or hundreds of thousands or even luckily millions of them, which cannot be directly learned using the model we have now, simply because we have billion users and billion levels of items. So the transfer learning idea is that how we can making use of the tasks we learned on predicting users' clicks, like, dislike, to actually improve the task of predicting users' response. So note here that there are many other types of transfer learning. For example, like cross-domain transfer learning, where the input could be on different space. In this case, the input actually can be on the same space, which is for like user item context space. So there are many approaches of doing transfer learning. One common approach is called off-the-shelf, meaning that we directly grab some of the model from trained from the source task and then plug it into the target task. And there are also some work on representation learning, where they try to learn the representation that can be either invariant or adapt to the target task from the source task. And there are some recent advances on continual learning, for example, and also model distillation that provide this new set of technology that we could use to do better transfer learning. So first, I'm going to talk about some of the off-the-shelf work maybe in literature or in academia. So the first provide a good data example where we show that we have a very complicated tuned machine learning model, which is SVM on image classification. And what the paper does is actually directly grab some CNN train from a larger other much larger data set, and then directly plug it in, and then use that to do the prediction, and it outperforms this heavily hand-tuned SVM model with feature engineering and anything like that. So similar idea has been used here at Google as well, where we basically we could directly grab some of the hidden embeddings we trained in the learning to rank model I mentioned before, and then concact maybe some of the hidden layers, or concact some of the embeddings we use, for example, like video embeddings or video features, and make it like a large feature input to the model that we can use to predict the user response, and then freeze the part of the model from the source model and train maybe a simpler model to predict user response. Another line of work is basically related to how we can learn a better shared representation to do transfer learning. So this area mostly have been called domain adaptation, where they can have very similar tasks. However, the domains are different, meaning that the probability of giving this label on this task can be different on these two domains. So one line for work is try to introduce some regularization term to learn feature representation invariant to different domains, and also. The other line work is actually we can learn two sets of feature representation, but we can add some regularization to make them the two feature representations similar. And I think the key difference is about how we do better parameterization, because in the invariant feature representation, we have less knob to tune the feature representation adapt for the target task. Well, in the similar feature representation, because you have this independent learned feature representation as well as regularization term, basically you have more parameter for the target task. And one example I want to point out here is using some of the recent advances on adversarial learning to do domain adaptation. And for example, if we can add an adversarial task just to predict the source of the domain of which this input of which this input comes from, with the adversarial loss backpropagates to the shared representation can actually help the representation being learned, unlearn the effect of using some of the feature representation to predict which domain it is. So it is quite handy and easy to implement within our multitask framework to do transfer learning. And in parallel, there are some recent advances on transfer learning and more also on model compression, for example, like distillation, that can be used for transfer learning. At the left-hand side, we show what we call the continuous learning or adapter network, where first being proposed by doing continual learning, but also can be applied to transfer learning, where it's simply adding adapter network on the comparing to the off-the-shelf approach. Basically, it grabs the embedding and add a linear transformation or some other kind of transformation to transform it into the target task, and then use that feature and then use the transform feature to the target task. Basically, you can think of that as adding some more parameters for the target task, so that you have flexibility of control the capacity when the capacity need to be used for source task is different from the capacity need to be used on target task. On the right-hand side, we show how we can making use of distillation to do transfer learning. I think as Rishi mentioned above, something about distillation basically is the technique firstly being used for model compression by introducing a student network, learning from the teacher network. And the teacher network is basically going to provide supervision to the student network. And this idea can also be used in transfer learning, where we can, instead of sharing the model parameters, we directly utilize the supervision from a teacher model trained from source task, and then do some projection on some of the hidden embeddings and transfer that knowledge onto student network. So it's quite handy because there's no dependence on the model we trained before. Okay, so to sum up multitask learning and transfer learning, we talk about some of the concepts, where the difference here is multitask learning learns multiple tasks in a single model, while transfer learning only cares about target tasks, but you need to transfer some knowledge from source tasks. And the use cases are like, both of them have multiple use cases, where multitask learning has been used in any type of machine learning applications need to have multiple prediction targets. It's extremely useful in search and recommendation. And also for transfer learning, similar things happens as well. Instead of you have a task with fewer labels, and you can improve the task by transferring the knowledge from tasks with larger number of labels. And there are still a lot of open challenges here, including how we can measure, because we are training the model, training different objectives altogether, how we can improve the training dynamics of multiple tasks by exploring different model architectures, how we can understand how task relatedness and imbalance of the data can affect multitask model. And how we can, for transfer learning, how we can tune model architectures and also hyperparameters so that we can have a perfect model architecture setup that adapts from the capacity of the source model as well as can be transferred, make best use of these model parameters for the target model. So that concludes my talk. If you guys have any questions, feel free to talk to me in person and also send me an email.
Perfect. Thank you.
Thank you.